So welcome to this week. This week's lesson is going to be on magnetic fields. Uh, the plan is for each week there will be an instructional video like this posted on Google Classroom, as well as practice questions in your workbook. As you're working through those practice questions, if you do run into any problems, take a picture and throw it up here in the stream of our Google Classroom, and then I can respond to that with another video and be a little bit more specific about any questions that we might have. So also under here, there will be an assignment posted each week. Sometimes it'll be relatively small, but that's going to be kind of how we work assessment going forward. So it will be important to kind of respond to those assignments. And again, if you are not able to access the Google Classroom for whatever reason, or if that's a barrier, like please send me an email and we can kind of figure out another way of delivering the course to you. Because we still want to make some progress over the next 12-ish weeks. And this is kind of the format that it's going to look like. If you do look at the Google Classroom, and I said this in the email, there is way more here than what we're actually going to talk about. If you are looking for more stuff to do, this is here for you, but we are going to focus on just the big ideas. That's what you will be assessed on, and there isn't anything outside of that. But everything else that you see here is like that's the course, but we are definitely going to look at a more targeted, specific way of delivering it. Okay, so today we're going to be talking about magnetic fields. Everyone kind of knows how magnets kind of interact with each other. If you have a magnet and a compass around home, maybe you can kind of pull it out and start playing with it. I don't know if you have those anywhere, but maybe even just a fridge magnet and a compass. But we know that like when we take compasses are tiny magnets. We can take those and they will interact with magnets. You probably grew up with magnets, playing with them. You know that if I take two opposite poles together, they're going to stick together and they're going to attract. If I flip that around and have two like poles, well then we know that those actually repel. And that's probably something that you've experienced in your life already. And that's kind of one of the reasons why magnets are so fun when we're at younger ages. If we were to take iron filings and actually throw them over top, so these are just pieces of iron, you end up with actually this picture. So here you have two unlike poles and you can kind of see the attraction between them. And then we also have two like poles and you can see how they actually repel each other. So you can actually see these field lines if you were to put something magnetic over top. And so this kind of helps us to explain why things attract or why things repel. Just like when we had oppositely charged charges or similarly charged charges, they would attract or repel each other. And we explain that with an electric field between them. A magnetic field is the same thing. So we describe kind of the space between these magnets as being a magnetic field, and that magnetic field allows us to picture that attraction or that repulsion and helps us to explain why it can take place over large distances. So these are our magnets. One thing we might notice too when we put a compass in there is the compass will also interact with the magnetic field. So if I were to have these, there are my magnets, now I were to put the compass in between, I would see that the north pole of the compass is attracted to the south pole of the magnet, and vice versa. If I were to move this compass around, so maybe I end up in this region here, the compass would actually start to flip because, again, that compass needle is going to be attracted to the south end of the magnet and repelled from the north end of the magnet. And so then on the back end, it might look something like that. Now, what a compass does in this magnetic field is important because that is actually how we define magnetic fields. Just like with electric fields, we use a positive test charge to define it. A magnetic field, we use the direction that a compass will face as the actual definition of the field. So an electric field, again, we use a positive test charge to define it. In a magnetic field, we use just a compass. So our compass needle is the definition of the direction of a magnetic field. So I put that compass in that magnetic field. The direction that that compass needle points is the direction of the magnetic field. So that's how we define magnetic fields. So magnetic fields are relatively strong. We'll look at some calculations in the coming weeks, but they can attract or repel. We can't separate poles from each other. So that idea is just if we were to take a magnet and cut it in half, we're not going to have a north and a south. We're going to have two magnets with north and south poles. And there's some videos I'll show you later which maybe will describe that a little bit more when it comes to permanent magnets. So we draw magnetic field lines just like we saw in that video with that picture with the iron filings. So magnetic field lines, just like electric fields, they show kind of the direction of where a compass needle would point at all these different places in space. So this is maybe my iron filings. I apologize, I'm using a mouse to draw today. I do have something coming that will make it easier to actually draw on top, and so it will be less tricky. But so here's my compass needle. If I were to put a compass needle here, it would be pointing towards that south pole. So the direction of the magnetic field at that point would be towards south. If I were to put my compass on this side of the magnet, well, now that north end of the compass needle is repelled, or the south end is attracted. So the direction of the magnetic field at this point would look something like this. And then as I put my compass needle at these different places here, it's also going to be pointing in these different directions. So the compass needle at these points is actually going to be pointing along these field lines and along these field lines here. So that's really how we define an a magnetic field, is where a compass needle will point, and it will always be away from north and towards south. That's kind of the big idea. So a compass needle is always going to point away from the north end towards the south end at these different points in time. We can see that in between this south and north end of the magnet, they actually interact with each other as well, and we could possibly see that if we look at these diagrams, although they're kind of cut off and it's a little bit more difficult to see. Magnetic field strength uses the symbol B, and it's measured in Teslas. So a Tesla is how we measure magnetic field strength. We use B as a symbol, and we'll be looking at some formulas and calculations again in the coming weeks. Just some general strength. The Earth's magnetic field, so is 5 times 10 to the negative 5 Teslas. A small fridge magnet is 0.01 Teslas. All the way to, like, if you're on a neutron star, the magnetic field strength would be 108 Tesla. And it's kind of a measure of that twisting force. So this compass needle is going to twist. It's going to have a torque. That's kind of what it's talking about. How much does it actually twist? That's the magnetic field strength. Now that does have some implications for our Earth here. Right? If I were on the surface of the Earth and I were to have my compass, right? So I have my compass right here. I would find that the compass would point this way, right? So here's the magnetic field of the Earth. This is what my compass needle looks like. So maybe I'll draw this way. So here's my Earth's magnetic field. These lines again are very ugly. In future lessons they'll be better. So there's my Earth's magnetic field, and if I had the compass needle in those different places, that's what it would look like. But as we get, so if we take that compass needle and put it down here at the geographic South Pole, you'll notice that this looks very similar to what happens when we are at the actual North Pole of a magnet, right? It's always going to point out from north and towards south. So if I were to have a compass needle at the South Pole, it would be pointing north. It would be pointing out from south and towards north. And then at this North Pole here, the geographic North Pole, it's actually behaving like a South Pole. So if we were to say that the Earth is a magnet, and this is sometimes hard to kind of wrap our heads around, but if the Earth was just a giant magnet, the geographic North Pole is actually the magnetic south, and the geographic South Pole is actually the magnetic north. So Santa Claus is at the magnetic South Pole, and Antarctica is at the magnetic North Pole. And that again is that's really just the nature of how we define magnetic fields and the fact that we define magnetic fields using the direction a compass needle were to point. Uh, so it's really just a product of that. So geographers and physicists didn't get together and say, okay, this is how we're going to define north and south. They did it separately, and so our geographic maps have the North Pole as being where Santa Claus lives. However, because we define things based off of where a compass needle would point, the geographic North Pole is actually the magnetic south. So yeah, in summary, magnetic fields show how two magnets can interact with each other over a large distance. I know like charges repel, so if I were to have a question like this, A and D are not correct because A is opposite poles and they're repelling. D is two like poles and they're attracting. Uh, and I also know that the direction of the magnetic field will always be out from north and towards south. So if I were to look at this diagram, all the field lines should be going to the right towards the south pole. In C is probably correct because it's going out from north and it's showing that repulsion as well. So the practice questions that you're going to work on this week. So this week will be a relatively like small week in terms of kind of what we're doing practice question wise. So it's page 136, 137 in your workbook, numbers 1 to 8. If you have any questions, please post them in the Google Classroom. And also, if you do have any questions from previous weeks, like I know that the previous week was kind of a mess, some of that uniform field stuff, like if there's some stuff that you would want to tidy up a bit when it comes to questions that you had, I would love to answer those questions there as well. There will be an assignment coming, and that will be posted there as well.